Hello there, and welcome to this presentation for the computer vision assignment and theoretical foundations in particular. In my report, you'll find the practical bit, but for this presentation, we'll focus on the theoretical a bit. So the objectives of this presentation, we're going to mainly look through edge detection, corner detection, and the Hough transform line parameterization. And to start with, our first objective was edge detection. So we're going to look at how you can define edge detection, how you can identify an edge in an image, how image detection works and therein image edge detection, and the various methods of edge detection. So what is edge detection in particular, right? So we can start by defining what an edge in itself is. An edge, when it comes to computer vision, an edge in an image is a significant local change in intensity or color between neighboring pixels, and this is often associated with a boundary or a transition between different regions in an image, right? Edges may arise from various sources such as object boundaries, surface texture, and illumination changes. It doesn't necessarily mean, as people would typically think, that an edge is where two things meet, or that, as we'll see later, that's more associated with a corner in computer vision than an edge. An edge is just a boundary or a significant local change in intensity or color between neighboring pixels, right? Because in computer vision, we know that our images are usually made up of pixels. So this is an example image that we're going to use in this presentation. As you can see, this image has what you'd call a couple of different colored um, squares, right, that are on top of each other. So we're going to use it to try to determine what is an edge, what is a corner, what can we do about it, etc, etc. So based on our previous image, how can we determine an edge? How can we identify an edge, right? Edges are usually identified by detecting discontinuities in brightness or color in an image, right? So when you're looking at your image and you see that there are changes in color or changes in brightness, that usually represents that there is an edge in that image, or at that place where that change in brightness or color is going to represent an edge. And techniques that we usually use are techniques such as gradient calculation, right? Where if we do a gradient calculation for an image, we would be able to find the magnitude of the gradient, which indicates the rate of change, and the direction, which indicates the orientation of the edge that is used, right? So from our example image, we can see that after applying different practical methods, for example, in our assignment, we had to implement an edge detection algorithm, right? So if we were to apply that edge detection algorithm to our initial image, we'll be able to see that our edges are now outlined. As you can see, our edges are now outlined. Our original image, as you remember, was just different colored boxes on top of each other, different colored squares. But now we can see that we've been able to actually isolate out all the colors and be able to identify that now what you see in white are our edges. So it doesn't matter if it is the upper edge, the left, right, or lower edge, but it's clearly showing us that there are four edges for each of the different boxes that are in our image here, right? So how does edge detection actually work, right? Image detection, first of all, involves us processing the pixels of an image to identify the features such as edges, corners, or regions of interest. This process typically involves applying filters or mathematical operations to enhance certain characteristics of an image so that these make the features more distinguishable. For example, from our previous slide, we were able to see that we had an original image that had different colors of squares on top of each other, right? But for us to be able to actually identify edges in this image, we were able to apply different filters that were able to remove the different colors, and we're able to just remain with two colors, black and white, where we could see that our edges were clearly outlined by the white color, right? Then image edge detection in particular, right, works by applying mathematical algorithms to detect changes in image brightness, which we just talked about. That we get our image and we're able to use our pixels to identify what the image is about. Then we use different algorithms, which we'll cover later, to be able to actually isolate out our edges and corners. So what methods or what different methods can we use to actually detect edges in our images? There are gradient-based methods. Like we said, we can use gradients to compute edges, but what methods actually use this particular form of technique? Gradient-based methods compute the gradient magnitude and direction to identify edges, right? The very first method that we're going to look at will be the Sobel operator method. The Sobel operator method performs spatial gradient measurement on an image, and it emphasizes regions of high spatial frequency that correspond to the edges. And you might be wondering, how does this work? How it works is that it uses two 3x3 canals, one estimating the gradient in the x direction, which is usually what we call the horizontal direction, and the other in the y direction or the vertical direction. These kernels are then convolved with the original image to calculate the gradient approximations. As later you'll see, you can be able to apply convolution algorithms to images to be able to actually identify lines. And then from these, the gradient magnitude and direction can be determined, right? And what applications do we have for this particular Sobel operator method? It can be used in scenarios where gradient magnitude is of importance, right? Since it's using gradient. It considers the intensity variation in both horizontal and vertical directions, and often results in thicker edges. And then we can go ahead and look at our very next method, which is the Canny edge detector. The Canny edge detector is a multi-stage algorithm designed to detect a wide range of edges in images. Applications for this particular method is that it's widely used due to its effectiveness in detecting a wide range of edges, right? It's known for its precision and ability to detect weak edges and produces thin and well-defined edges. As you can see, certain algorithms or certain methods are not very well with finding those thin or unproperly defined edges. But certain ones like Canny edge detector are able to use these multiple stage algorithms to be able to determine even the weakest of edges. And how does it work? It works usually using noise reduction, which typically is a Gaussian blur that is applied to a filter, is applied to this image to filter out noise. And then a gradient calculation is used to determine the intensity gradients of the image. And then suppression is used to thin out edges to ensure that they're sharp. Then a double threshold determines potential edges by thresholding, and edge tracking by hysteresis finalizes the detection of edges by suppressing all the other edges that are weak and not connected to the strong edges, right? So we can see that this particular algorithm is a very popular one because of its ability to apply those multiple stages to be able to detect even the weakest of edges. Our next method is called the Prewitt operator. It is similar to the Sobel operator method in some way, as it is used for detecting vertical and horizontal edges in images. How it works is that it also uses a 3x3 convolution kernel, one for detecting changes in brightness in the horizontal direction and the other in the vertical direction. Its application or applications is that it's usually used for high frequency emphasis and edge detection. Like we already said, it's similar to Sobel, but might be less sensitive to noise, because one of the problems that Sobel had is that it can be very sensitive to noise in images. But ProWit performs a bit better even when there is noise in the image. And our last but not least method for this presentation is the Laplacian of Gaussian, or what they usually call a log. It combines the Gaussian smoothing and the Laplacian operator. How it works is that the image is first smoothed with the Gaussian filter to reduce noise. So they first remove the noise with the Gaussian filter, and then the Laplacian operator is applied to detect edges. This operator calculates the second derivative of the image, highlighting regions of rapid intensity change. And remember, the more you're able to identify these regions, the more likely you are to detect all the edges in the image. Its useful applications usually include scenarios where the detection of edges as zero crossings is advantageous, and it's effective in detecting edges with a more rounded appearance, and is capable of highlighting finer details in an image. Like we saw for our previous ones, like ProWit and Sobel, they worked better with um, images where the edges are going to be have vertical and horizontal, but this Laplacian of Gaussian method works very well with scenarios where images even have rounded appearance. So that is what we had for edge detection. And then our next subsection for this presentation is corner detection. Now that we know what edges look like, which are usually, like we said, uh, discontinuities or changes in intensity or color in an image. But what about a corner? What is a corner? What role does corner detection play in computer vision systems? How is a corner detected in an image? And corner detection approaches is what we're covering in our next part of this presentation. So to begin with, what is a corner and corner detection of an image? A corner in an image is a point with two dominant and differently edge directions, right? Since we already know that in an image, after we identify edges, they can have directions, horizontal or vertical, right? So a corner becomes a point with two dominant and different edge directions. It's a point where the gradient changes direction abruptly, often corresponding to an interesting or important feature in an image. And corner detection is the process of identifying these particular points or these corners in an image, of course. It plays a crucial role in computer vision tasks such as object recognition, tracking, and image stitching, as we'll see. So for example, from our original image, after identifying our edges, as you can see, using our red arrows, you can see that those particular ones actually corners, right? Because we're having different directions of edges. You can see some, for example, the very first arrow, you see that, there is an horizontal and then a vertical one that's going down. So that point where they meet is a corner in our image. And what is the role of corner detection in computer vision systems? Let's expand on this a bit. It's important for feature extraction, right? Where corners are considered good features for extraction as they represent points where image gradients have significant variation. This makes them suitable for tracking and recognizing objects across different frames in a video or different viewpoints in multiple images. Then the second one is image matching and registration. In tasks like panorama stitching or 3D reconstruction, corners provide reliable key points to match corresponding points across different images. Then in object recognition and classification, corners can be used as key points to build descriptors for objects, aiding in recognizing and classifying objects using different scenes. And then last but not least, motion detection and tracking. Corners are stable points that can be tracked over time, making them useful for tracking objects in video surveillance, augmented reality, or robotics. Then 3D modeling. In computer graphics, corners can help in reconstructing the shape and structure of 3D objects. And finally, in navigation and mapping, particularly in robotics and autonomous vehicle systems, corner detection aids us in understanding her surroundings and behavior. So when we start looking into self-driving cars, corner detection will be an important thing because it helps us know that you've reached the end of this particular road. You need to turn. Then in 3D modeling, motion detection and travel and tracking in all different applications of corners. And how is a corner detected in an image, right? We can use these three methods. Gradient variations, like we already said, we can use gradient directions to determine corners, where a corner is typically characterized by a change in intensity in both x and y directions. And the number two, in window-based analysis, where we use where many algorithms actually can use a small window that moves over an image, checking for variations in intensity within the window, and that signifies a corner in an image. And then last but not least, we can use a response function, which is a mathematical function that can be used to quantify the likelihood of a point being a corner, because not every point in an image is a corner, but we can use a mathematical function that can quantify this likelihood. And this function returns a high value for points with high variations in gradients. Then next, we can go ahead and look at corner detection approaches. We have a couple of approaches that we're going to cover, but to start with, we have the Harris corner detection, which identifies corners by detecting the change in intensity for a displacement of a small window in all directions, right? And how does it work? The algorithm involves computing a Harris matrix that measures the corner response and identifies corners based on a threshold value. It's widely used due to its relative simplicity and effectiveness in detecting corners for a wide variety of applications. So this is one of the most widely used methods in detecting corners. Then second, we have the Shi-Tomasi corner detection. It's a bit similar to the Harris detector, but it changes the way of computing the score, making it more robust in certain situations. How it actually works is that it uses a minimum eigenvalue of the gradient covariance matrix to decide if the point is a corner. It is often preferred for tasks like tracking due to its robustness in detecting strong corners. Next, the next method is called FAST, or Features from Accelerated Technique Test. This particular approach focuses on high-speed corner detection, ideal for real-time video processing. The way it works is that it examines a circle of 16 pixels, for example, around the candidate point and identifies a corner based on a specific intensity pattern. It is popular in real-time video analysis and applications where computational efficiency is very crucial. The next one is called SIFT, or Scale Invariant Feature Transform. This particular approach extracts key points or interest points from an image, which often include corners. It is robust to changes in scale, rotation, and illumination. Then finally, we're going to look at our Hough transform line parameterization. Here, we have to prove that the line equation P equals to x cos of theta plus y sine of theta. The line equation in polar coordinates is that, as we just said. In the Hough transform, a line in the image space can be represented as a point in the parameter space, or the Hugh space, or the Hough space, using the equation P equals to x cos theta plus y sine theta, where P is our distance from the origin to the closest point on the line, and theta is our angle of the vector perpendicular to the line. Each image point, say xy, results in a sinusoidal curve in Hough space. The amplitude of the sinusoidal relates to the value of P, and its phase relates to the coordinates xy. The phase of the sinusoidal corresponds to the angle theta based on the line connecting to the point and the x-axis. So to look at our parameterization choice, why use p and the angle distance p and the angle theta versus using m, using the slope intercept m and c. The parameterization is used instead of the slope intercept because it can represent vertical lines where m would be infinite and is less sensitive to horizontal lines. Because if we use the slope intercept, m would be infinite. The relationship between mc and p theta is given by m is equal to negative cosine of theta divided by sine of theta, and c is equal to the distance p divided by the sine of theta. Our parameterization choice using distance p and theta instead of m and c offers several advantages. Expressing m and c in terms of p and theta. These advantages include the slope m can be calculated as the tan of theta, and the intercept c can be calculated as the distance p divided by the sine of theta. The maximum absolute value of p and range for theta. Maximum p. The maximum absolute value of p corresponds to the distance from the origin to the farthest corner of the image, which is the square root of w squared plus h squared, where w is the width and h is the height of the image. And range for theta, the range for theta is typically from 0 to pi radians, or 180 degrees, covering all possible orientations of the lines. Now let's plot these sinusoids and find the intersection for our points 10, 10, 20, 20, and 30, 30, which defines the line and then calculates MC for this line using Python. As you can see, we're having three different graphs, and they're actually intersecting or intercepting at 0.